Hello, folks. Good afternoon. I promise that I'll do my best to keep you awake because after lunch. So my name is Julio. I'm from Red Hat, Brazil, and today I'm going to talk about massive data sets and how you can train some models. And this is basically a high-level presentation, and I'm going to use a use case that we did with an oil and gas company. Okay. This is the agenda. I will do a real quick introduction, and then I will explain about some preprocessing techniques, some data dependency issues, some accelerators for massive data sets, and some conclusion and some previous results, okay? And this is a funny fact. I am a kernel engineer at Red Hat. I don't know if you probably know CentOS Stream 10. I have worked with kernel CentOS Stream 10 kernel in the past. Right now, it's a different kernel maintainer, but I have this background, and this presentation is basically about my Master in Science project that I did, and the focus was the high performance computing and AI, focus in seismic data. Okay, but I know this is a specific area of science, but in general, this talk is more widely, so you can use some techniques in regular pipelines, in regular AI pipelines if you wish, okay? And what is the problem? So this Brazilian oil and gas company came to us and presented the problem, and the problem is, okay, I need to do seismic phases analysis in massive seismic data. I am a guy from computer science. I don't know what does it mean, but okay, I'm gonna do a quick presentation, and I promise that you understand in quick slides, in real quick slides, okay? So the first question is, what is this task, okay? I don't know, I'm not a geologist, I'm not a geophysics, so what does it mean? And the second problem, what is seismic data, okay? We are talking about LLMs and other AI pipelines dealing with images, but what is seismic data? This is a standard seismic data, okay? This is basically, well, there are several standards for seismic, okay? If you are feeling an earthquake, you're probably dealing with different seismic data. But regularly, if an oil and gas company wants to drill a hole in the middle of the ocean, this company will map an area and probably will produce this data here, okay? And usually, the format of this data is called SEGWI, okay? And it's basically, it was designed on 70s for basically improve the data acquisition and using some techniques for doing that. And quite often, it's a very, very, very huge data. And it's very interesting because this example here in the left side is a small one. It's 1.3 gigabytes, but it's technically a small one, and it's a public data. It represents a data from the North Sea, a small region, and it's very interesting because it's a cube, okay? And the depth axis, it's basically one wave that represents this signal that is mapping the area. And basically, this axis represent the emitter from until the end of not the bottom of the ocean, but until that wave can reach, okay? And what is seismic phases analysis? It's very simple. It's just to categorize each layer in their respective structure, okay? It looks like simple from human beings, but actually it's not, because this slices has some geographic dependencies between them, okay? So in general, seismic phases analysis is a way to categorize seismic data to find similar structures, reservoir, and others, okay? And now, talking about pipelines in general. So probably if you are training an AI model, you recognize this workflow, okay? You have some raw data, you do some kind of preprocessing stages to trim the data or something else, and then you have your curated data, and then you apply some transformations in order to train a model, okay? This is a very simple pipeline that you probably know. And Sometimes you want to run your pipeline in your local machine, in a local machine with a GPU, or even in some specific environments like HPC systems, cloud systems, or others. Okay, if you want to train your model just for fun, you can do in your local workstation. But anyway, there are several examples that you can use. But talking about seismic precisely, we have our SegWi data. We usually do some data cleaning to remove some samples that we don't like to use. Especially in seismic, I presented you a cube, but in general it's more like a polygon. So if you want to convert this polygon into a cube, you probably want to fill the remaining data with zeros, for example, and then you have a cube. And once you have your data, you usually extract some features to understand more about that data. And once you have the features, you can classify your data and do the seismic phases analysis, okay? Okay, and now go into some pre-processing techniques, okay? Again, seismic data or the SegWi format is not regular. It's a polygon. So it is like this, it has this format because, again, it was designed to enhance or improve data acquisition, okay? So imagine a boat in the middle of the ocean trying to map an area to understand if that area has oil or not. So the boat goes doing zigzag, and you need to create an algorithm to map this boat behavior into a cube, okay? That's why this data is very hard to parallelize. It's not a regular data, it's irregular data. So we need to be capable of transforming this data into a better format for parallel computing, okay? And because of that, it prevents us to use this data in a distributed environment, for example. So how could you do that then? Okay, we can convert SegWi into a more suitable format for parallelization, if you wish. Okay, and there are several options for that. We have ZAR, we have X-arrays, we have HDF5, Parquet. But for seismic, we have some specific formats that basically combines features from the existing data sets. One example is MDIO. I think this format was developed by British Petroleum. I don't recall exactly the name of the company. But basically, MDIO uses ZAR as a backend. So you can convert SegWi into a ZAR format if you wish, okay? And we have SeismicC and many other formats that basically uses these libraries behind, okay? And why we want to do that? Because we want to use some two important features of these modern formats, okay? We want to use chunking, okay? We want to split this data in smaller parts and manageable blocks. And this allows us to use different parts of the data set independently, okay? In nodes, threads, if you are using a local workstation. And furthermore, we can use the lazy reading, okay? When the data is not loaded immediately into the main memory. And it gave us the option to read the data on demand, okay? And basically, by combining these two features, we can transform this huge big cube into small pieces, okay? And then we can read these slices on demand, and we can see how this data looks like, for example, in a local workstation. And we can handle gigabytes of data in one workstation with only 16 gigabytes of memory, for example. And then, as I told you, we can split this data and process the small chunks of data in several independent nodes, threads, or CPUs. So we can apply some transformations independently, okay? And now we have a design that we can use in a high-performance system instead of using a SegWi, which is terrible. And talking about this use case with this oil and gas company, we studied a lots of libraries and formats that we could use to process this data. And in the previous presentation, we had a nice example that is using Ray. But in this project specifically, we decided to use Dask because most of the transformation that this type of company does in their data is basically some calculations, and we can do easily with NumPy if we want. And Dask has a nice API that integrates with NumPy very well, so we try to use this feature. That's why we decided to use Dask and not PySpark or Ray, for example. Okay, so in talking now about data dependencies, okay, I presented you the regular pipeline that you probably know, but the real world is not so beautiful, okay? We are not Alice in Wonderland. Usually when we are dealing with this kind of pipeline, especially the seismic one, we need to deal with different types of transformations in the data. Some transformations has dependencies between them. And when we are doing, or when we are handling in this situation, we can increase the number of data that we are generating. One example is, okay, if my raw data has 800 gigabytes and now I want to do 5 transformations, so I can generate up to 4 terabytes. Maybe I can use 1 terabyte as an example to help me with the calculation, but this is one example that I can generate data even more, okay? So I can lose the control of the pipeline and the memory occupation. And this is very interesting because when we are talking with this company, the solution that they are taking is for each transformation, we generate a new file or a new data set. It's like a checkpoint, okay? So imagine how many files we will have at the end of the process. This is not efficient, okay? So one of the main objectives of this work is to do the whole operation dynamically, okay? And avoiding trying to checkpoint transformations or the output of transformations in files, which is very, very weird, okay? And now talking about this specific part that is the feature extraction, in seismic, okay, feature extractions, when we are trying to highlight data in a seismic data, we usually call it seismic attributes, okay? And again, extracting features, doing data augmentation and other transformations usually can create significant amounts of data or intermediate data. Especially in the seismic field, usually this type of company uses some black boxes transformations because for some reason they develop a feature extraction that cannot be shared for some reason. So we don't know how this code performs. What is the performance, if there is any optimization, if there is some temporary structures that increases the memory usage. So it's very hard to understand the behavior of this type of operation. And if you are using a chunk-based approach, this new data can quickly overwhelm the memory if it's not handled correctly. So you need a strategy to handle this chunk as well, okay? And design or create a pipeline that understand your needs and the requirements to define the better strategies to calculate the transformations is definitely a key aspect of your pipeline. So this is what we want as a result of this work, okay? Okay, and now I'm going to present you some 2 use cases and some 2 real problems that we faced in this work. And one example is about a feature extraction that was trying to do or compute a signal processing feature. And it's very interesting because if you have already worked with signals, if you are calculating, for example, a fast Fourier transform, you need to keep the time axis, right? So if we are using a chunk-based approach, we cannot split the data in the time axis. So this is a requirement for us. Okay, so what is the solution? okay, we can keep the access, but split the chunk even more to keep the size of our chunk, okay? This is a nice solution. This is a nice strategy, okay? It's perfect. But if now we have a feature that calculates a filter in the raw data, and now we have a window that calculates for each step a new value, and what is the problem, okay? If we are doing it, or if we are handling chunks, we need to share the borders with each chunk, because we need to calculate we need to calculate the filter in the borders. And okay, what is the problem? We can cause an IO-bound problem, because if we are in a high-performance system computing, sharing the borders with other chunks can cause a lot of data transfers, okay? So one solution is exactly similar to the previous one. We can preserve one access to reduce data transfer, or if there is no other way, we can use some techniques or technologies to speed up our transfers, like InfiniBand networks or UCX frameworks, and so on and so forth, okay? And now, the big question. What happens if we need both features to train a model, okay? What will be an efficient chunk strategy for our pipeline? Again, we can combine both requirements. We can share the left and the right borders with each chunk and keep the time access, for example. So this would be a nice chunk strategy that we need to consider when we are dealing with this type of pipeline, okay? And again, it reduces the number of data transfers because we are just sharing the left and the right borders. And one important hint here, be careful, because if you are sharing too many data, you can also increase the chunk size, and it impacts the memory usage at the end of the process, okay? And this is a nice chart, okay? If you want to know what is a good strategy to adopt in my AI pipeline if I need to deal with chunks, okay? You need to consider, okay, this is a small chunk, and if I need to share borders, how many data transfer it will be produced, okay? But if I'm using a very, very, very big chunk, it can cause problems. It can cause problems to my memory or to the memory of my system. So a good strategy is something right in the middle of both curves, okay? And I call it the sweet spot. So if you don't know, if you're still trying to understand how is the behavior of your pipeline, try to do something in the middle, okay? It's always a nice or a good strategy if you don't know what to do. Okay, so moving to accelerators for massive data sets. We have heard a lot about GPUs, using GPUs. It's almost impossible to think in AI today without using GPUs, but GPUs are very, very expensive, okay? And if you spend the money buying GPUs or buying some nodes or cloud environments with GPUs, you want to take advantage of it. So you want to use it effectively. And if you want to do this effectively, you want to use libraries that help you to handle data in GPU. So you have several options like QDF, QPy, Dask supports QPy internally, and tensors, obviously, if you are creating a pipeline with PyTorch. So make advantage of libraries that supports GPUs, okay? Another important aspect of datasets is how you can read files. Usually, the regular workflow when you are reading a file and using the data in your GPUs, you read the file from your local file system, you load it into the main memory, and then you move this data into the GPU memory. But it can cause some bottlenecks to the process, okay? And to avoid this kind of thing, we can use some other technologies like GDS. It's called GPU Direct Storage. And basically, it provides you some mechanisms to read the data from your file system directly into the GPU memory, okay? And this is exactly what I'm talking about, okay? Now you don't need to use the main memory to read the data. And if you are dealing with a ZAR, for example, you can use an API or you can use a library called KVKio. I think it's a Danish word, so I don't know how to pronounce this name, but it's part of the Rapids AI library. Rapids AI is a library from NVIDIA. So if you are dealing with ZAR, you can use KVKio to load the data directly into the GPU memory, okay? And the conclusion, this is very interesting because we now, after applying all these techniques into an existing AI pipeline for seismic, we are capable of running faster, okay? Usually a seismic phases analysis span about 20 hours, 10 hours, depending how the pipeline looks like. And now we are running at least 10 times faster using these types of techniques. We applied several techniques in several existing pipelines. We used a lot k-means, cohonens, self-organizing map, and XGBoost. I know k-means is so old, but it works like a charm for seismic problems. And we also were capable of using the same strategy in deep learning models like UNet and WiseNet. And one of the most interesting part of this work is no matter if we are using or we are creating AI pipelines, the features are always important for companies like that. And speed up this process are very, very, very important for them. So we also were able to speed up several of these feature extraction tasks. And all this job, we have used a data set that represents the Brazilian pre-salt data. There are several data. One of them is the Santos Basin. It's a very important data, but it's confidential, it's not public. But it has almost 200 gigabytes or even more. I don't recall exactly. And this is a little bit weird, but it's also interesting. Now we were capable of running this pipeline in a machine that has low memory, for example. We tested a 32 gigabytes data in a workstation that only has 16. It's 10 times slower, but now it's possible to read and train a model. And we were some precursors of several research projects that are still ongoing right now. And now that because we are capable of process huge data, people now can do other research using that. And all this project was encapsulated in a framework that we call DASF, okay? And now I'm gonna explain a little faster what is DASF. DASF is the acronym of DASF, is a recursive acronym. DASF is an accelerated and scalable framework, and the premise of DASF is to accelerate and scale code easily with few code directives, okay? You can see how it works by accessing our repositories. There are some documentations and examples there. And it contains some lessons learned that we did with this Brazilian and oil and gas company, but it's not only for seismic, okay? If you want to deal with wearable data, you can. If you want to deal with image data, you can, okay? Because the most important thing of this framework are the techniques, okay? Not the code. DASF was primarily based on Dask, as I told you. It also uses NVIDIA's Rapids AI library to include some GPU accelerators. And the recent versions also supports Ray, okay? And right now, there are some researchers that are still, I think they are finishing their researches, and we have plans to integrate some memory profilers in DASF, especially to understand what is the behavior of the chunk. I can do a quick example. For example, PyTorch Lightning has some heuristics to understand what is the best chunk dimension for that problem. And we are working on similar profilers, okay? And If you are curious, this is how DASF looks like. We can create some operators and transformations here. We can create the pipeline, and then we can execute the pipeline. The code will basically convert the lines of code into a high-level representation using graphs. And that graph will be executed in a target that could be a local workstation, a cluster, a high-performance computing, a cloud system. And what defines where is where we want to run this pipeline, it's exactly the red line. You define the executor, and that's it. That's only the directive that you need. You can reuse this code everywhere, okay? And that's it, folks. It's just a brief presentation about this specific area. And if you have some questions, I'll be open to it.
So why you need the Dask?
Yes, it's a good question, because when we are trying to solve this problem related to seismic phases analysis, we try to study a lots of libraries that probably can help us to do our job right. So we try to use, for example, Spark, we try to use Ray, and because of the concepts that this company gave us, we thought that Dask would be the easiest way to solve their problems. Okay, not sure if I answered your question.
So then anticipatedly, I think probably like you mentioned, there's some other Python library can also probably resolve the problem.
Yes, probably. But again, the problem that we are trying to face was a little bit hard. And for some reason, Dask was solving our problems very well. So we decided to keep Dask as our solution for that problem specifically.
Okay, I see. So if you kind of change the slides to the how you augment the data, the transfer.
Oh, sure. 1 second. I'm trying not to shake my hands here to cause problems to the. Okay.
Yeah,
No.
yeah, here.
Yeah.
So you augmented the data, right? And how did you augment the data? I'm curious.
Yes, actually, we are not. Augmented the data is just an example. But for seismic, we are not augmented the data. Actually, in some specific cases, we are. For example, there are some researchers or research that we want to generate seismic attributes using some deep learning techniques. So we need to use augmented data. But for these specific pipelines, for this specific problem, we are not augmented the data. Okay, we are using just the raw data, but we are trying to, for example, normalize the data, reducing some outliers, and things like that. We are just trying to clean the data, okay?
So then what transform means here?
Transfer is basically situations like doing feature extractions, trying to normalize the data is a transformation, because you have the raw data and now you have a different data that is not equal. Okay?
Yeah, just like you said, probably zero mean or univariance. If you go back to the accelerator slides.
Oh, sure.
Yeah. Out of curiosity, why you need the accelerator here?
Yes, this is another interesting question, because when we were debugging the pipeline, for example, just talking about massive data sets specifically, okay? When we are talking about massive data sets, reading data is very important. It's a very time-consuming task. So we need something to improve this data or this reading. And that's the reason why we need accelerators. Because mainly all this task we are doing on GPUs. And if we are reading from file system into the main memory and then moving to the GPU memory, it is a lot, the path is so long and can cause us bottlenecks, okay? So we need something to accelerate this reading process.
Oh, I see. So what is the accelerator here then?
Yeah, accelerator here is a way to accelerate the reading process.
Oh, okay.
And move the data from file system into the memory target, which is the GPU.
So it's a mean of kind of to read the data efficiently,
Yeah.
rather than any kind of specific kind of hardware to accelerate the data.
Yeah, you will need GPUs and probably some kernel modules to do that, but it's in general.
Okay, I see. Yeah, so I fully understand now. Yeah, thanks.
Okay.